Hi, welcome to module number 27. In the previous module, we started talking about machine learning. We looked at two classifiers, and now we're going to chat about decision theory. Uh, Decision theory deals with going beyond classification. Now we're going to minimize a loss function. We're not going to choose with a classifier between two different classes, but we're going to perform an optimization. One example would be a squared error loss function. We've seen a vector beta of coefficients, and the error as a function of the beta coefficients is going to be a summation over yn, measurement number n, minus xn transpose. Recall, the x, the data, can be high dimensional, multiplied by this hypothetical beta vector, and each of these y minus xn transpose betas is going to be squared, all right? So to make it clear, xn transpose beta is going to be our prediction, a linear predictor for the yn, and we're going to evaluate the squared error at sample n and sum over all the capital N squared errors. Now, you'll note that this approach, squared error, emphasizes, accents the larger errors. So imagine, suppose that the typical error is 0.2, and one of the errors is 1.5. So 1.5 is roughly a factor of 7 more than 0.2, and with squared error, that one location with a significant error is going to count 50 times worse, okay? And this problem is even more severe for, let's say, cubed error, or error to the power of 4. Imagine with error to the power of 4 that one of the locations is 7 times larger error. Well, 7 to the power of 4 is going to be 2,000 something, right? So that means that the algorithm, in trying to optimize betas that minimize the error for squared error loss function, it'll put quite a bit of emphasis in those outlier samples. And for to the power of 4 error, it'll put the majority of the emphasis in a small number of outliers. Now, for squared error in particular, and we're going to see this in part in an example on the next slide, suppose that you know the statistics. Knowing the statistics is referred to often as a Bayesian case. So Bayes meaning you know the probabilities. If you know the statistics, the approach that minimizes the squared error loss function is conditional expectation. In particular, our estimator y hat for the noisy observation, or the noisy observation y, is going to be the expected value of y conditioned on the data x. And x, of course, are going to be explanatory variables, and y is going to be what we're predicting. And I'm really saying for squared error, conditional expectation is optimal. What about other types of error? So I've already said that if we have, let's say, error to the power of 4, we're going to be overemphasizing the outliers. So what if instead of that, we look at absolute error, error to the power of 1, absolute value? So here's our example. The error function, which is again a function of the coefficients vector beta, is going to be a summation over the absolute value of the error, the unexplained part, the difference between yn and xn transpose beta. For absolute error, the smaller errors are going to receive more weight, whereas earlier, if there was a factor 7 in the pointwise error, and with squared error it was roughly 50 times more important, and with to the fourth it was maybe 2,500 times more important, with absolute error it'll only be 7 times more important. So yeah, of course we're going to pay more attention during the optimization of the betas to the larger errors, but we're not in any way going to be overwhelmed by the larger errors. And what we're going to soon see in an example is that optimizing the absolute error leads to a median type of estimator. Now, medians can be interpreted as more robust. So it could be that you have data and you have a small number of outliers, and those outliers totally dominate error to the power of 4, and they somewhat dominate squared error. Well, with absolute error, because the answer is the median, outliers don't matter. They just count as one more point. Now, what about the binary classification problem that we've already discussed using the nearest neighbors approach and a linear classifier? Suppose that you're again in the Bayesian regime where you know the probabilities. In that case, you're going to be selecting the most probable class. So you know the probabilities, you calculate the probability of being in the red class, the probability of being in the blue class, you take the larger one. All right, so here is our comprehensive example. We're going to evaluate both a absolute error and a squared error for the following data. Y is a vector and its elements are 2, 1, 1.5, 2, and 17. Let's begin by looking at squared error. So we want to choose the beta that minimizes the error, okay? Now, this is such a simple example that this may not be quite so obvious. What I'm really asking for, I want a constant estimator. There's no x here, okay? There's no x. I'm asking you, give me a constant such that the squared error will be minimized. Okay, so let's go through this step by step, and we're going to begin with the squared error case. So we want a constant. Let's call it alpha, or you know, let's call it a scalar beta. We want a scalar beta such that summation over n yn minus beta squared is small. Okay, so how do we find this constant? So I'm telling you it'll turn out to be the average of the numbers, and the average is conditional expectation, but we're going to revisit this point in a few minutes. Let's do it first of all by brute force. So we have a function of beta. Let's just call it f of beta, okay? Now let's articulate f of beta. F of beta, again, it's a summation of samples minus beta square, so it's equal to 2 minus beta square. And then we have, the next sample is 1, plus 1 minus beta square. The next one is 1.5. 1.5 minus beta square. The next one is 2. So let's just multiply the previous 2 minus beta squared by 2. And the final one is 17. So 17 minus beta squared. Now, by the way, you could take beta minus 17. You could take 17 minus beta. When you square it, it's the same. So let's continue. So this is 2 times 4 plus beta square minus 4 beta plus 1 plus beta square minus 2 beta plus, what's 1.5 square? 1.5 square is 2.25 plus beta square minus 2 times 1.5 times beta, that's 3 beta. And finally, 17 square is, well, it happens to be 289, but you know, frankly, because we're going to optimize beta, we're soon going to take a derivative with respect to beta, so you don't care about the constants, okay? I just want to put this out there that you don't need to calculate the constants. So 289 plus beta square minus 34 beta. 34 is 17 times 2. So let's think about what we have. We have constants. Plus we have, or rather minus, beta is multiplied by 2 times 4 and 2 in the next expression, 3 in the next expression, and finally 34. And finally, beta square is multiplied by 2 in the first expression, 1, 1, 1. So we have 6 in total. And recall that the length of the y vector, 1, 2, 3, 4, 5. Am I missing something? Hold on. So is it 5 or is it 6? 1, 2, 3. It's 5. Yeah, sorry about that. So now we want the derivative with respect to beta. And by the way, oftentimes you'll see in the literature, in papers, with respect to is often abbreviated as WRT. So the derivative is f prime of beta, let's just use the f prime notation, is equal to, well, constants, as I said earlier, the derivative is 0, and we have minus beta multiplied by, well, the derivative of minus beta is -1. So basically, 2 times 4 is 8, plus 2 is 10, plus 3 is 13, plus 34 is 47, so minus 47. And now we have 5 beta squared. And the derivative of beta squared is 2 beta. And overall, we have 10 beta minus 47, and we want it to be 0. This means that beta is 4.7. And that's what I wrote earlier, that beta hat, the optimal beta is 4.7. Now, recall, optimal estimator is conditional expectation. We don't have data X here. We just have Y. And because of that, the optimal estimator is conditioning on nothing. And we take the expected value of beta, or rather of Y. So the optimal beta is the expected value of Y. But what sort of expectation? Because we don't know the statistics of Y, we don't know the distribution. It's an empirical average. So 2 plus 1 plus 1.5 plus 2 plus 17 divided by 5 elements. 2 plus 1 is 3, plus 1.5 is 4.5, plus 2, 6.5. 6.5 plus 17 is 23.5 divided by 5. So let's think about it. 20 divided by 5 is 4. 3.5 divided by 5 is 0.7, so we have 4.7. So bottom line, empirical average gives us the best beta, and it minimizes. Recall, both times we got 4.7. It minimizes the squared error. All right, so that's squared error. But what about the L1 norm of Y, or rather the L1 norm of Y minus beta? Okay, so let's derive this. So with absolute error as a function of beta, again, beta is a constant estimator, and error as a function of beta is the L1 norm of Y minus beta. What's the L1 norm? It's a summation over absolute values. So this is 2 minus beta. Now recall, the number 2 appears twice, so I'm multiplying it by 2, plus absolute of 1 minus beta, plus absolute of 1.5 minus beta, plus absolute of 17 minus beta. Now, taking the derivative of an absolute value it yields either -1 or +1. Derivative of error of beta, for each term, we have -1, +1, and we have the corner point. At the corner points, the derivative is undefined. So now let's try to actually do this by plotting things. So let's plot. The horizontal axis will be beta, and the vertical axis will be the derivative, f prime of beta, and the smallest number is 1. So below the number 1, let's look at all these things. So 2 minus beta is as beta is increasing, it is going down. So let's say for beta equals 0, this expression is 2. For beta equals 1, it's equal to 1. 2 became 1, so we have a negative derivative. So we have a negative derivative, twice because of the multiplication. We have a negative derivative up to the 1 for the second term and the third term and the fourth term. So we have negative derivatives. So how many negative derivatives? 5. 2 here, 1, 1, 1. So we have a derivative of negative 5. Around 1 and up to 1.5, we have a discontinuity. So the 2 minus betas are still negative. The 1 minus beta, now the term 1 minus beta, it was going down. And then at 1, it started going up. So now we have a positive derivative. And these two guys are both negative derivatives. So 4 negatives, 1 positive, and we have negative 3. Now what happens between negative half and 2? Between negative half and 2, and this is not, clearly I'm not drawing to scale. The 2 minus betas are both negative, so I have two negative 1 derivatives. The 17 minus beta is negative, so I have 3 negative derivatives, and I have 2 positives. So overall, my derivative is negative 1. Things become interesting from 2 to 17. Now, you can imagine that at 17, the derivative is plus 5, because I have 5 terms that are all increasing. But what about from 2 to 17? So the expression 2 times 2 minus beta is going to be positive. And then we have the 1 minus beta is positive. Well, the absolute of 1 minus beta, its derivative is positive. The only one that's negative is the 17 minus beta. And overall, my derivative is 3. All right, so we're left here with the following situation. Recall, we want the beta where the derivative is 0. Now, because of the discontinuities and derivatives, they're undefined for these values, 1, 1.5, 2, and 17. The derivative is never 0. However, now I'm changing color. Here, the derivative went from negative 1 to plus 3. So 2 is the optimal beta. Beta hat is equal to 2. Now, I wrote that earlier, and I said that it's going to be the median. So let's think. What's the median of these 5 numbers? 17 is the largest. Then I have 2 2s. Okay, so median means out of 5 numbers, the third ranked number. One of the 2s is the third ranked number, so the median is indeed equal to 2. Now let's try to understand, why is that the case? At the median number, suppose that you have n plus 2 numbers above it, and n divided by 2 numbers above it, and n divided by 2 numbers below it. It's probably not exactly n over 2. It might be n over 2 minus half, or minus 1, or etc., but approximately n divided by 2. Half of those terms are going to have a positive derivative. Half will have a negative derivative. So overall, the derivatives at the median are going to be balanced. And again, the median is uninfluenced by the 17. Earlier, because of the 17, the empirical average of these 5 numbers was 4.7, which was larger than any of the numbers except for the 17. You have 4 numbers that are clustered between 1 and 2, and all of a sudden a 17, but our estimator is 4.7, way outside the range of 1 to 2. On the other hand, in the second example, the median is 2. It's in the range, at the edge of the range, 1 to 2. So bottom line, the median estimator is more robust to outliers. The 17 could be interpreted as an outlier. And overall, this is the advantage of optimizing for absolute error. All right, so that's it for these slides, and we'll continue next time.